This video has been sponsored by Nuage Networks. For more information on the Nuage Virtualized Services platform and how Nuage is delivering consistent policy-driven automation across data centers, the WAN, and branch locations everywhere, please visit nuagenetworks.net and follow us on Twitter at Nuage Networks. We hope you enjoy the session.
After watching this video, visit ipspace.net/sdn to learn more about software-defined networking and overlay virtual networks. The first question you should ask is, what network services, because we are talking about networking, will your cloud offer? And it depends totally on who you think your customers are. Some easy customers think web hosting, need a single VM, and they'll run Linux or Windows on that VM and some embedded database, some web server, and some scripting environment. For these customers, the network connectivity is exceedingly simple. I have one VM, I need a public IP address, I'm done. And then you have the other type of the customers, typically enterprise customers or people deploying scale-out applications in public clouds, where you have this multi-layer application architecture using web servers, app servers, caches, databases, who knows what else. And in these environments, you always have to provide some load balancing. In the ideal case where the application guys know what they're doing, you just have to provide the load balancing in front of the web servers, because it's pretty hard to solve that problem without a dedicated load balancer. But of course, this could also be solved by the application guys if they use Squid or Nginx or whatever else for load balancing. And then if the application is written for a scale-out environment, that's all you have to provide. In many cases, particularly when enterprise applications get deployed to private or public clouds, they need someone to insert a tier of load balancers between any two tiers in the application, because the application developers just didn't think about this. And even if we don't need the load balancers, usually people want to have some security or some firewalling functionality between the application tiers, sometimes even between the VMs of the same tier, which brings us to either firewalling or security groups that we'll discuss in maybe half an hour. What a typical complex application needs are multiple logical segments. I'm not saying they are VLANs, I'm not saying they're subnets. They could be implemented with security groups, but every complex application would need multiple logical segments. Hopefully, the application has been written in the last few years, so it only requires IP connectivity within a segment and between segments. Sometimes you still have to deal with the old stuff that requires MAC level connectivity for heartbeats or what have you. Then you have to provide routing between segments. If you're talking about layer 2 and layer 3 implementation, then obviously you need bridging within a subnet and routing across subnets. Or you may go down the path of Microsoft Azure or Hyper-V and provide just the layer 3 connectivity implemented with host routing. Then you need, as I mentioned, load balancing or firewalling, some baseline isolation within a segment that's usually done with security groups, and you need some connectivity to the outside world. More or less all overlay virtual networking solutions offer some sort of layer 2 forwarding. A VM sending a packet to another VM in the same segment is sending the packet straight to the other VM's MAC address, so we have a unicast or broadcast if we're doing ARPs MAC header in there. That gets encapsulated into an IP packet, and here the crucial question is, how do we get the destination hypervisor's IP address in that IP packet? And then it's sent over to the other hypervisor. I haven't seen any implementation of overlay virtual networking that wouldn't have distributed layer 2 forwarding. The question is, however, how is the control plane implemented? So how do we distribute MAC to VTEP IP mappings between the hypervisors. Some solutions use multicast, most solutions use some control plane, and then the question is, how scalable is that control plane? An interesting question: do you know of any widely deployed application that requires MAC connectivity between different tiers of servers? I'm not aware of anything that requires MAC connectivity between tiers of servers, but within a single tier, people still use Microsoft Network Load Balancing. Well, obviously not on Azure or Amazon clouds because they don't support MAC layer connectivity. But in large private clouds, I am seeing people who still use Microsoft Network Load Balancing, and that thing is using MAC layer tricks. So yes, sometimes we still have to support layer 2 connectivity, unfortunately. If, on the other hand, you have multiple subnets in the application stack and you need some sort of routing between them, then you have to make sure that that inter-subnet connectivity doesn't become a choke point. And you know that some popular cloud networking solutions, like maybe OpenStack, at least till the recent release, or CloudStack, use layer 3 forwarding implemented in a VM, which is just a Linux virtual router with multiple interfaces connected to multiple virtual segments and doing IP forwarding between the segments. The VM-based forwarding has its own inherent performance limitations, and having a VM inserted between multiple segments obviously creates a choke point. If your application is primarily sending the traffic to the outside world, then you more or less don't care. But if you have lots of east-west traffic, or in my case, because I've turned the picture around, it would be up-down traffic between the segments, then you should avoid centralized inter-subnet forwarding. In those cases, you really need an architecture that has distributed layer 3 forwarding. Yet again, those things could be implemented in VMs, although admittedly I haven't seen anyone doing distributed layer 3 forwarding in a VM, but I'm positive it will eventually pop up. There are people who have implemented distributed layer 3 forwarding with Linux namespaces and default Linux TCP/IP stack, and there are people who are solving this solution with in-kernel switches. You should always prefer the later solution because the Linux TCP/IP stack has some performance limitations that are well known to anyone who has to write high-speed network function virtualization appliances. You're usually limited to a few gigabits of forwarding performance through Linux TCP/IP stack. On the other hand, we know that the latest releases of Open vSwitch easily push more than 10 gig through a Xeon server, and an Open vSwitch doesn't really care whether you are doing layer 2 or layer 3 forwarding. Sample products that implement layer 3 forwarding in kernel: Juniper Contrail, Microsoft Hyper-V, Nuage VSP, and VMware NSX. All of these do layer 3 forwarding in kernel. Next question. If you're doing layer 3 forwarding, then obviously if that's all you do, the router, because every VM is connected to a router, will do the ARP processing as well. But if you're doing a mixed layer 2 and layer 3 forwarding model, so if you're implementing the traditional network architecture with double quotes VLANs or subnets and then inter-subnet distributed forwarding, then maybe you can reduce the amount of flooding inside a subnet by intercepting ARP requests and caching ARP replies. This is how a typical solution would work. Let's say that C is sending an ARP request for D. In a traditional layer 2 only architecture, you would see an ARP request, a broadcast going out. In a typical layer 2 plus layer 3 architecture, the ARP broadcast would still go out because this is within the same subnet. So the layer 3 device doesn't care about whatever is going on within the subnet. On Hyper-V, by the way, the ARP request would be intercepted by the kernel module and answered locally, but that's a different story. So what the mixed layer 2 and layer 3 forwarding solution could do is it could intercept all ARP requests, even those that are local, reply to them from the local ARP cache that is either built by the controller or built on demand based on the previous ARP replies. And then you have two options. Either you flood the request when there is a miss in the local ARP cache, or you might say, well, controller is the source of all truth, and in that case, the local layer 3 gateway would contact the controller on ARP miss, get the information from the controller, and then reply to the ARP request. And if even the controller does not have the information, it can flood the ARP request. There are at least two platforms that do exactly this: VMware NSX for vSphere and Nuage Networks VSP. If we continue talking about distributed forwarding, there's always the network services. I'll spend more time on the network services later on. I just want to mention how the scale-out architecture of network services could solve some performance problems. Scale-out load balancing is mission impossible because there is a shared state that is tied to the outside IP address. So the net rules, because load balancing is actually net. The net rules for established sessions have to be distributed across all instances of a scale-out load balancer. And you know that that is a really hard problem. Midokura is working on solving that. They were solving that with a central database. I don't know how well that scaled. I have no real data on how well they perform load balancing in real-life networks. No one else is doing anything on this front because this is really a problem that is maybe not even worth solving. Scale-out firewalls are way more common. They are also much easier to implement because all the shared state is tied to a single VM. State that VM A needs in the firewall can be totally decoupled from the state that VM B needs in this distributed firewall. So all the sessions that are valid for A could be listed here, and all the sessions that are valid for B could be listed here. Scale-out net is somewhere in between these two, and you'll see that there are some interesting creative solutions that you can use. Almost all large-scale virtual networking products offer some sort of traffic filters or firewalls, distributed scale-out firewalls that you can insert between the virtual switch and the VM. What is dependent on the product, though, is whether this filter is actually stateful firewall filter, which means that it's also checking sequence numbers and things like that, or just a reflexive access control list, which just matches outgoing TCP SYN requests or UDP requests with incoming return packets. And for most cases, reflexive access control lists might be good enough because today's TCP stacks handle TCP sequence numbers pretty well. Some solutions offer only standard access control lists, and there you might have the well-known TCP established keywords to solve the return traffic problem. There are two ways these VMNIC firewalls are usually implemented. Like with layer 3 forwarding, they could be implemented in kernel or in a VM. Do avoid the solutions that implement these filters in a VM, because then a single VM limits the performance of the whole hypervisor. Some sample solutions: Nuage VSP, VMware NSX, OpenStack or CloudStack on KVM. All of them use stateful or stateful-ish solutions that are implemented in kernel. For example, OpenStack or CloudStack would use iptable and ipset. Access control list only solutions, Microsoft Hyper-V has equals built in the new release, as does VMware vSphere 5.5 or Cisco Nexus 1000V. On ARP and NDP, there's an interesting question. Most SDN solutions do not support IPv6 yet. Will they be able to deal with the risk of neighbor discovery tail saturation due to potential high number of IPs in IPv6? I guess the question for Dimitri would be, because I really don't know the answer, does Nuage VSP support IPv6? And if not, what are the plans to support it?
Currently, the current release does not have support for IPv6. This is scheduled to come sometime in 2015. The interesting thing here is that when you are looking at scale for this type of solutions, the amount of state that needs to be maintained on a specific hypervisor, it's only driven by the number of VMs that are in the current hypervisor and their associated networks. So if we assume that a hypervisor has something like 50 VMs, and these 50 VMs belong to 50 different networks, and there are 100 VMs, let's say, in each one of these networks, you end up with a state that is about 5,000 entries. And this is by no means an issue in maintaining that type of state. Again, the hypervisors don't need to keep state for all VMs into the system, but the state is filtered down to what they need to keep for the VMs that they are serving.
Also, on IPv6, where you might have multiple IPv6 addresses per interface, you will never have more than maybe a dozen addresses, but not even that. So you might get a problem that is an order of magnitude worse, but not more than that. Next question on the ARP caching. ARP can be intercepted by in-kernel layer 2 switch or layer 3 forwarder. Is there any specific advantage in one or the other? No, it doesn't matter who intercepts the ARP request as long as you don't do flooding. Answer, and I need to read this one because I mentioned it, from Dan Dumitriu from Midokura. Midokura no longer uses the central database for connection state. They use state push in-band between Midonet agents. So they don't use a central database, but the hypervisors push state between them. For a scalable data plane, as you've seen, we need distributed layer 2 and layer 3 forwarding. It's ideal to have local ARP handling, either by caching ARP requests and replies or having pure layer 3 solution like Microsoft Hyper-V. And we should have distributed network services. Security groups are the easiest one to do, implemented in hypervisors. If you like this video, go to ipspace.net/cloud to explore other overlay virtual networking webinars.